Hello and welcome. I'm John Watt, and this week we're tackling the titans of Mother Nature: earthquakes, tsunami, and volcanoes. Ever wondered how much we actually know about what we call acts of God? Plenty of Kiwi scientists have, and as usual, I'll be travelling the length and breadth of the country to meet them. First up, we're off to the capital. The motorway behind me runs in almost a straight line from Wellington to Lower Hutt. This is because it sits directly above one of Wellington's 5 major fault lines. These faults are the result of 2 of the Earth's 15 tectonic plates crashing together beneath us. So I'm off to the National Museum, Te Papa, to get a seismic perspective on New Zealand. Hamish Campbell is a geologist and helped create the Awesome Forces exhibition. Hamish, we've got this wonderful floor map of New Zealand. What's interesting about New Zealand's seismic activity?
Well, I think the most interesting thing is that New Zealand straddles a plate boundary. We can actually see what happens when 2 plates meet. And if we take a walk, here we are at the bottom end of the South Island. This is Milford Sound, and this is the plate boundary. This is the Alpine Fault that runs right up the western side of the Southern Alps, and then it veers out to the east, around Wellington, up the east side of the North Island. This is the point where the Pacific plate is diving underneath the Australian plate. So we're feeling, in Wellington, we're feeling the effects of compression and collision due to this process of subduction. Subduction meaning to be led under.
About 100 kilometres off the east coast, the Pacific plate is forcing its way under the Australian plate. The world's largest and most destructive earthquakes occur at these subduction interfaces.
The last major earthquake in Wellington was in 1855. That was on the Wairarapa Fault, some 25 kilometres to the east.
And was that a large event?
That was huge. It was greater than magnitude 8.2.
What kind of damage can we expect from an 8.2 magnitude or greater earthquake?
We know that from what happened in the 1855 earthquake. Buildings were damaged, and of course our slopes will fail. So all steep slopes around the Wellington region will start breaking up and collapsing.
But aren't there a lot of houses built on slopes in Wellington?
There are, yeah, that's right. So we're expecting quite a lot of damage. We get a movement in Wellington, a big earthquake, about every 200 years.
But if that's every 200 years, surely the next one will be, what, in the next 40?
Yeah, we could indeed be due for a big one within the next 40 or so years.
This is Napier and Hastings after the infamous 1931 earthquake, and we can see the kind of devastation that can be caused. Since this, many buildings have been built with earthquakes in mind. But the holy grail of earthquake research is to predict when and where the next one will strike. Can we predict when it's going to happen?
We can't. In terms of trying to anticipate an earthquake, say at 10 o'clock next Tuesday, we're just miles away from being able to do that.
Okay, so we can't predict earthquakes yet. But at Victoria University, there's a scientist who's up for the challenge. John is investigating one of the hottest topics in seismology: slow earthquakes or slow slips.
Slow slip event is something very similar to an earthquake in that one plate moves with respect to the other, but it takes place over several days or weeks or months or even years.
Observing these slow slips may be the key to predicting sudden, violent earthquakes. Slow slips happen as the subducting plate plunges deep into the earth and begins to melt. This chocolate bar's been cut to represent the interface between 2 tectonic plates. It's all warm and soft, just like the rocks deep below the Earth's surface. And my hands are going to represent the forces that are acting on those tectonic plates. Let's see what happens. So as I push together, one of them just becomes a gooey mess. And this shows ductile behaviour. Now I'm going to show you brittle behaviour. To do this, we take the same material, a chocolate bar, but now it's been frozen to represent those cool, solid rocks that reside on the Earth's surface. Let's see what happens. So it's a lot harder to push together, and when it goes violently, just like an earthquake. It is between the brittle and ductile areas where the slow slips occur. But the challenge is, how do you measure something that is moving so slowly? John solved this by looking to space and is using satellites to pinpoint the position of GPS receivers placed on these volatile areas to measure movements to the millimetre.
By just measuring your position every 30 seconds, for example, over long periods of time, you can build up a very accurate position of where you are. And then when things change, either there's an earthquake nearby or a slow slip, that's very easy to detect.
These slow slips have given John crucial clues as to precisely where the next big one might hit.
Where the slow slip tends to occur seems to delineate or to mark those patches of the subduction zone which are locked and where we think future earthquakes might occur.
The red areas show accurately when New Zealand's two great tectonic plates are locked together, producing enormous tension, and an earthquake must eventually strike. The source of Wellington's earthquakes is a plate boundary only about 100 kilometres out to sea in that direction. But it's not just earthquakes that Wellingtonians have to worry about, but the possibility of a huge tsunami. What are we doing to protect New Zealand from the kind of devastation that was caused by the Boxing Day tsunami in Asia? Recent tsunami have shown us just how devastating the combination of earthquakes and coastline can be. And here in New Zealand, we're not short of either. The Boxing Day tsunami captured the world's attention and devastated cities like Banda Aceh. Dr. Graham Leonard is trying to ensure New Zealand doesn't suffer the same fate. Graham, you're our tsunami expert. What's this contraption we've got in front of us?
Right. This is a highly technical tsunami model, and we've used a container that you might put your shoes in under your bed to try and show you the way a tsunami arrives at the coast and runs in over the land.
Why is tsunami different from normal waves?
A normal storm wave or wind wave is just disturbing the top of the water and in a little way, and it's something like that. They're just like a surf wave. So you imagine a surfer sitting right here, and those little surface waves coming in, and the wavelength on those is just a matter of seconds.
Let's see what happens to that surfer in a tsunami.
Right. And then look at the size of that wavelength.
Yeah.
And when it hits that slope at the coast, the wave ramps up on top of itself and it inundates, up to kilometres inland. This is massively sped up, so that wave would probably be coming for 10, 20, 25 minutes, and then rushing out for 10 or 20 or 25 minutes.
The biggest tsunami in the world are caused by locked subduction interfaces that build up massive forces which are suddenly released, creating these tragic tsunamis. Unfortunately for us, this is exactly the situation we have only 100 kilometres off the east coast of New Zealand.
We're starting with the instant that earthquake has occurred, and the ground here has snapped up. So the ground has gone up and the water has gone up and is red. As soon as I hit play, watch that.
And that hit in 5 minutes.
It did, and it's already wrapping around the coast, and we're still getting right in at Wellington.
And that's 20 minutes.
20 minutes. It's important to understand that 5 metres on one of these deep water models will get up to about 10 or 15 metres right at the coast. Then when it hits the land, it'll double again as it runs up on steep coastal lands.
What do you expect it to be once it curls around and hits Wellington?
Up to 30 or 35 metres, yeah.
To put that in perspective, the beehive is only 72 metres tall. So this tsunami would swamp 50% of New Zealand's Parliament building and cause massive damage to Wellington's CBD.
We can expect in Wellington and the southeast coast of the North Island the biggest tsunamis in the world.
It's kind of scary.
It is. It's very scary, and that's why we really want to prepare for it.
To help protect Wellington, Graham analyses the information from the computer models so he can come up with the all-important evacuation plan.
So here we've got a real tsunami evacuation zone map for Island Bay here in Wellington. And what we've done is taken a large number of those models and calculates how it's going to drop off inland, because we know tsunami drop off a certain amount every 100 metres inland.
The good news is that large tsunami are extremely rare, so Graham's maps are colour-coded. The yellow area is to be evacuated if the big one comes, orange in the case of a medium-sized event, and the red would have to be evacuated for small waves like those generated by the Chile and Samoa earthquakes.
We're aiming to have these kind of maps around the country, all looking about the same. So if someone moves from one place to another or is a tourist, they're already going to know from where they came from, what the procedure are and what to expect in their tsunami evacuation.
Graham, 15 minutes for the wavefront to Wellington. That must make your job extremely difficult.
It does in a way. It means that there isn't going to be an official warning. There just isn't time. But it also means there's going to be a strong earthquake felt in the Wellington region. So what we're doing is preparing the public to respond to feeling an earthquake or seeing something unusual in the ocean and evacuating in response to that. If you feel the earthquake, hard to stand up. As soon as the shaking stops, it's time to head inland. We're not going to be able to generate any sort of official warning in time to respond to that.
So you set us up and then it's up to us.
That's right. I'm the setup guy, and hopefully you're not the fall guys.
As if that wasn't enough, the subduction interface doesn't just cause earthquakes and tsunami. As the Pacific plate is forced under the Australian plate, it slowly melts and sends magma towards the surface. In fact, we can draw an almost straight line of active volcanoes from White Island through Rotorua, Taupo and Ruapehu. Auckland lies hundreds of kilometres to the west of this chain of volcanoes, in a completely different but extremely volatile type of volcanic area known as an intraplate hotspot. Behind me are Auckland Domain's playing fields, which actually lie in a huge volcanic crater. So, how much danger is our largest city really in?
I think that's an interesting thing.
This one piece will make 52 layers.
Watch on mobile devices or the big screen, all for free. No subscription required.
Dr. Jan Lindsay is leading the investigation.
There are about 50 volcanoes in Auckland, and these volcanoes are part of the Auckland Volcanic Field, where batches of magma have come up from the mantle and erupted in different places every time. That's why we have a field of volcanoes.
Exactly why it is so volatile in Auckland is unknown. The volcanoes here are unlike the volcanic belt in the central North Island, where pressure builds in a magma chamber. Auckland's volcanoes are much more sudden, unpredictable and dangerous because the magma rises straight through the crust, giving us little warning of an eruption. So it's not Auckland's volcanoes that are active, but the area itself.
A future eruption would have huge consequences for Auckland. Clearly the area around the direct vent would be devastated, so you might have a 3-kilometre radius around the vent, which is occupied by an explosion crater and a scoria cone, which would be complete devastation.
This is an imagining from Auckland Museum of what an eruption might look like. There is a good chance that it would occur underwater, simply because Auckland has so much of it, and this would explode into a huge cloud of ash, rock and gases. So how likely is an eruption like this?
In order to work out how likely a future eruption is in Auckland, we need to look at what's happened in the past to determine how often the volcanic field has erupted before. Being a geologist is a little bit like being a detective. You get to go out in the field, you take rock samples, you take them back in the lab and develop a story. So you can take it right from the beginning, from the mystery to the end, where you're sort of solving a problem. It's essentially like forensic science.
A crucial piece of forensic evidence is the sediment core. These preserve the ash that has fallen over Auckland for millennia. Dr. Phil Shane is leading this investigation into Auckland's violent past.
What you can see here, these are large volcanic ash layers from the central North Island. This one in particular is about 50,000 years old from Okataina, that's near Rotorua. When we find these types of ash layers, they're very useful because they tell us how old the sediments are, because those eruptions are very well dated.
How do you know what eruption that's from?
Many eruptions have a distinctive chemistry, like a fingerprint, so we can work out which eruption is which. This is an eruption from the Taupo region that happened 39,000 years ago. This darker brown area in the core here, this is some ash from a basaltic eruption in Auckland. Because it's so close to this Taupo eruption, we know that that basaltic eruption must have also happened about 39,000 years ago.
Unfortunately, this research has shown that Auckland is very erratic. Sometimes eruptions are a few hundred years apart, and sometimes tens of thousands. So how can Jan predict something so unpredictable?
In the Auckland volcanic field, because we don't know where the next vent is going to be, we're really reliant on the seismic technique, which is measuring earthquakes. As the magma rises up to the surface, it'll eventually start hitting more brittle rocks at about 30 kilometres depth, and at that point the magma will be cracking rocks apart to make its way to the surface, and it'll cause earthquakes, and we'll be able to detect those.
It's usually an All Blacks try that shakes the foundations here at Eden Park, but I'm here today to find out about vibrations that come from beneath the surface. Liam is developing a way to detect a volcanic eruption. Early warning could be the difference between life and death for hundreds of thousands of Aucklanders.
We're at Eden Park right now, and we're here because beneath the south stand there is a 380-metre borehole that's been constructed that has borehole seismographs in it to try and record some of the movements beneath the stadium.
The Sky Tower stands 328 metres tall, but Eden Park's seismometer is 55 metres deeper. This depth isolates it from the rumblings of the city itself so that it might pick up the subtle vibrations that are the warning of an eruption sooner. So how does this system work? Liam, this isn't exactly the executive box at Eden Park. What are we doing back here?
So we're back here at the University of Auckland outside the physics lab, and we're going to have a look at our test borehole.
How deep's this borehole?
So this borehole is 25 metres deep, and what we use it for is to test our new design. So here's an example of a borehole seismometer. It's a bit smaller than the one at Eden Park. So all you really do is just lower it down into the hole. So what we would do is if it was a temporary borehole, we would sand it in, or if it was a permanent borehole, we would concrete it in, so we can get a good transmission of vibrations from outside the borehole.
When the ground shakes, the vibrations are picked up by devices inside the seismometer called geophones. However, they only work accurately in one direction, and we need a three-dimensional image. So here comes the clever bit.
So what we have here is an example of the internal workings of a borehole seismometer. This is the same one as the one we have at Eden Park. These are three mechanisms called gimbals, and these are for holding three geophones. As you can see, if we tilt this to the side, it keeps these holders here in the right orientation. So for this one here, we're looking at keeping it in the vertical orientation. This one here, it's horizontal in this direction, and this one here, horizontal in this direction.
So these gimbals keep the geophones pointed in the right direction. Combine the readings and you have a three-dimensional image of how the ground shook. Liam's computer shows readings from near the surface and near the bottom of the borehole.
So what you can see is at 26 metres, there's a lot more vibrations from surface activity, but at 383 metres, it's a lot clearer. You can see this little blip here, that is an earthquake that was recorded, which is totally swamped by the surface vibration at 26 metres.
That signal's tiny, you'd never see that in the surface.
That's right, so if we zoom in, we can see much clearer the earthquake signal. And again, because we've spotted it at 383 metres, we can almost make it out at 26 metres because we've had that deep sensor there.
There are other borehole sites across Auckland, so by monitoring the intensity of vibration at these sites, it should help to triangulate where exactly a volcano is about to erupt.
So that may be able to give us a bit more time to be able to deal with the coming eruption.
When it comes to volcanic eruptions, we immediately think of lava, but it may well be the ash that causes the most damage. So what can we do to minimise it? I've come to the University of Canterbury to have a look at some spectacular methods of research that may help to answer that very question. Dr. Tom Wilson is investigating volcanic ash.
Why we're so interested in ashfall is that it's the hazard that's most likely to affect communities during an eruption. Now, a lot of the time it's not a sexy impact. There's not going to be impacts to loss to life. There's probably not going to be too many spectacular failures, but it is an incredibly disrupting hazard.
Poisonous clouds of volcanic ash can easily travel hundreds to thousands of kilometres, as happened recently when an eruption in Iceland caused billions of dollars of losses as well as chaos across Europe. Ash particles can be harder than steel, making them incredibly abrasive to machinery. They are often coated with acidic salts that can kill vegetation and corrode metals.
Equally, when it becomes slightly moist, it becomes very electrically conductive, and that's been one of the big focuses that we've had recently, is characterising the electrical properties of volcanic ash.
So what do we got here, Tom?
This is an insulator, and so it's a high voltage insulator. This is what you'd have on a transpower pylon, which is transmitting high voltage electricity from the hydro lakes in the south, for example, all the way up to Auckland.
So, volcanic ash on the insulators could mean massive power failure. We're going to test this. So first we need to find out how many volts clean insulators should be able to take.
Well, Johnny's going to increase the voltage across the insulator here, and eventually a flashover will occur.
While that's ramping up, what exactly is a flashover?
Flashover is the unintended electrical discharge across the insulator.
The flashover is essentially a short circuit that happens when the voltage gets too high for the insulators to handle. How many volts are we going to hit?
We'll be looking at a flashover at about 230, 220,000 volts.
That was loud. The clean insulator was very effective. It failed at about 220,000 volts, which is good news because Transpower limits the voltage going through its lines to around 110,000 volts. But let's see what happens when we add ash and a little moisture into the equation. 90, ramping up, 100, there it goes. So the contaminated insulator failed at only around 100,000 volts, less than the voltage being carried by a Transpower line. This extremely dangerous situation actually happened here when Mount Ruapehu erupted in 1995 and 1996.
Volcanic ash fell on the Transpower lines running adjacent to Ruapehu. This led to cascading failure across the grid and short-term disruption to Wellington. This even led to a dialysis pump failing in Wellington Hospital as emergency supplies didn't come on.
So how's Tom going to solve this problem?
But ultimately we're quite excited about trying to design more efficient or ash-proof insulators. And so that'll involve looking at the surface of the insulator itself, so this one's a glass one, and even changing the shape of the insulator itself, so whether it's a more dipping structure so the ash comes off quicker. These are all things to explore in the future.
We love living in a country with great icons such as Rangitoto, but we also have to live with the violent forces that created them. Our scientists don't have all the answers yet, but they're painting a more accurate picture about just what our planet has in store for us, so that we can plan for the inevitable. See you next week.